welcome to our conversation on quantum and AI, Quantum Lit, the game changer in AI race, hosted by Global Alliance on Sustainability and AI, Gasai. My name is Helen Teplitska. I'm a founder and president of Gasai and chair and global managing partner of Index Group. I'm delighted to be joined by Gasai Director of Technical Education, the ethical AI guy from Chesty, and a truly power-packed lineup of speakers. This is exactly how this panel was profiled in a comment on our announcement today. So today we're gonna focus on convergence of quantum computing and artificial intelligence. Together, we will cut through the hype and skepticism, highlighting real-world emerging applications of quantum mechanics and AI to explore how these technologies transform industries and redefine problem solving. With no further ado, let's start. Tom, the floor is yours.
Thank you, Helen. Okay, let's start with Bob. If you can spend a minute and introduce yourself and explain what you do.
Sure. My name is Bob Sutor. I've spent over 40 years in the industry, 39 years of that with IBM, most of it in IBM research. For example, I was the head of mathematical sciences, but I was also with IBM Quantum when we were really getting it off the ground for 6 or 7 years. After 39 years, I realized I was allowed to leave. I didn't have to stay forever. And so I joined a small company, which was about 2 orders of magnitude fewer people. So that was exciting, but it was also in quantum computing, quantum sensing, some quantum communications and things like this. Spent a little time as an analyst. Now I am just an industry gadfly, consultant, advisor, analyst, author. I wrote the book Dancing with Qubits, and have been speaking an awful lot about this quantum and AI, however it is we put those words together in some order. So it's a fascinating.
All right, Bob. How can quantum computing technologies and AI work together?
Most of the time when people think about quantum and AI, they are thinking about, well, artificial intelligence evidently requires a tremendous amount of computation. And everything they've heard in the popular press is that quantum computers will be these amazing supercomputers that can do anything in minutes instead of millions of years, things like this. And a lot of that's misunderstandings, right? So first of all, quantum computers only work well on certain types of problems, not any old problem you happen to have that come along, right? And so it's a good question to say, well, is AI in one of those categories to which quantum might be applicable? And that, I think, will be one of the major topics throughout the rest of the day. But let me kind of turn this around for 2 other application types that involve these 2 words. The first is, can we use artificial intelligence to actually make quantum computing better, right? And then maybe we hope someday use the quantum computers for AI. And that is absolutely yes, and absolutely right now, and absolutely for several years ago. And let me just give you a little bit of an example. It's an analogy. So many people, I think, have used noise canceling headphones. So you're on an airplane, you put on noise canceling headphones, you're listening to a book, music, whatever it is you're doing. And suddenly it's clearer. Suddenly all that background noise just goes away. Well, super oversimplified, what's happening is the headphones are listening to the surrounding noise and subtracting it out, right? So if we want to make this seem a little bit more AI-like, we say, oh, okay, well, we are picking up the patterns of the noise, right, that surround us and are intelligently using that to really subtract out and make clearer what it is we are supposed to hear, right? So in the same way, quantum computers, because the world is quantum, and I'll tell you, nature just wants to completely mess up our computers, right? Particularly quantum computers here. we can use AI with some of the noise information to make quantum computers work more precisely with fewer errors. All right, so that's the first application. Second application is AI and quantum in the same workflow. Right. So by this, I mean, if you think of what happens in a bank, right, or any big company, it's not like they won't run one algorithm. It takes data in and the answer comes out and then we're done. It's lots of little components that are all connected together. And data is flowing in and out of them. It's entering from other places. That is, some is fed out of one, fed into another. It's very complicated. I think a lot of people in quantum, or a lot of people focused on algorithm, just think about one component. So the idea is in this great big collection of different types of computation, some may be classical, some may be high performance computing, some may be AI types of calculations, and some may be quantum, right? So they're in the same neighborhood, I like to say, right? And once again, people are starting to explore that. Microsoft's done some interesting work on that. IonQ has done some interesting work on that. Basically, anybody who understands the notion of workflows and how this data can be improved by particular types of computation. But I think just to kind of end this part, the key question, and where I think the massive amount of hype is, is quantum computing used for AI. My position is it's a research topic. It's promising for great reasons, but it's so overhyped.
What are the challenges that you see using quantum for AI?
Well, I'll tell you, one of the fundamental problems is we cannot load a lot of data into a quantum computer. Quantum computers today are not error corrected, which means that as they are running, they are losing what we call coherence. That is, the information that is held is becoming more chaotic, noisy, right? It's almost like you do a calculation, right? And 2 minus 1. Instead of getting the answer is 1, you get 1.01. That's not quite right. If you did a little bit later, you'd get maybe something like 1.5 or something like that. So this noise causes problems in that we cannot load a lot of information into a quantum computer, classical information. And also, we can't do many computations with that information, even if you could get it in there. So the key problem is, if you happen to have a problem that doesn't use much data and doesn't require much computation, hey, quantum today is perfect. But great AI problems that don't use much data and don't require much computation are kind of rare, and we could probably just compute them classically anyway.
So there's a lot of companies talking about AI and quantum. Is it something that's going to take years to actually refine?
I think there's some very interesting research results. I recently surveyed the companies that are actually doing this, quantum for AI, and roughly speaking, they're between 20 and 25. Almost all of them are quantum computing vendors, right? There's a lot of academic research, but of commercial companies doing it. And the reason is because they want to show that their hardware is useful for something that people may care about. And what is a bigger buzzword today than AI, right? So showing that, wow, I'm in the AI game, right? I'm playing it here. My computers will be really useful for this really important thing that, by the way, is getting more than 10 times more funding than quantum computing itself, right? So you'd have to be kind of a fool to not somehow connect your quantum computing work to artificial intelligence if you're actively going after funding, right? And again, that's reasonable. It's hard to get funding, right? The science takes time, engineering takes time, but it's why people tend to exaggerate a little bit about what's going on. But I do want to emphasize, as a research project, as a research program, there's very interesting work going on. And the sort of programming model for quantum is so different from classical. It's almost like you're a carpenter and somebody gives you this amazing new set of tools to use, right? And you're very excited. You say, well, you have to learn how to use the tools. And basically, you can only use it on really big projects. But there's potential there, but let's not go too far.
That's good. Okay, I guess let's move on to Ariel.
Yep.
If you'd like to introduce yourself and tell us a little bit about what you do and how you're doing it.
But can you hear me?
Yes.
Great. So yeah, my name is Ariel Wallano. I run a small consultancy called FinServe Experts. We work both in the solution delivery and public policy space. I've been advising emerging tech, governments and large companies on emerging tech for 20 years now. I've been an advisor to UK Parliament on blockchain and AI. Like Bob, I was a long-term IBMer before leaving and striking out on my own. More recently been hired by the likes of Google, Lloyd's of London, to look at their emerging tech. Started working at Quantum in 2019, specific focus on quantum resilience because it's directly related to some of the other security work we do. As of now, and to Bob's point, we aren't implementing commercial quantum computing projects, but we are helping companies plan their migration to a quantum resistant environment in advance of Q-Day, whenever that may happen to be.
Let's see, who are really the likely earliest adopters of quantum computing?
Well, so, like any answer to the future, I look at the past. So let's look at every single sort of major technical revolution since the internet itself, the web, mobile, robotics, IoT, blockchain, AI. Pretty universally, one of the very first industry sectors to adopt any new technology is criminal enterprise, and there's no difference here. Already, large criminal organizations are engaging in a behavior that's now referred to as HNDL, harvest now, decrypt later. They're downloading large amount of password hashes, encrypted data, against the view that sooner or later they will be able to decrypt this. And given how poorly people change their passwords, this is held. And the other thing to understand about criminal enterprises, they have a natural first mover advantage. They have no governance. They don't need to care about things like your regulatory compliance or even customer satisfaction, for that matter. And as decision makers, they are ruthlessly practical. So one could argue the fact that there is an investment being made now in HNDL, says the sector believes that this is going to happen. No one knows when Q-Day is going to happen. Bob advised us, that we should be skeptical about some of the claims that it's going to happen soon. I certainly have no evidence to dispute Bob's point of view on that. But what we can see is that criminals are investing in that capability now, in the belief that in some number of years in the near future, it's going to be possible to use quantum computing to access all of this encrypted data. So what it behooves us to do in response is to be ready for it, and we don't need to wait for the advent of quantum computing. There are now algorithms and encryption methods that have been certified by NIST as quantum resilient. If you think about the average companies runs anywhere, say, between 1,000 to 2,000 pieces of software. Some companies upwards of 20,000. Much of that portfolio is going to be quantum resilient in time. Zoom, which we're having the call on, is already quantum resilient. They completed that migration. Microsoft in their roadmap. Okay. Other things like, say, SQL Server, maybe not in their roadmap, but they've got a modern pluggable architecture. So if SQL Server doesn't embrace quantum resilient encryption, you can plug in your own encryption algorithm. That's a capability. It's a little bit work. You've got more cost of ownership, but you can do it. But for any company, there's going to be, in our early research, and this is purely anecdotal, I wouldn't call it scientific evidence yet. But our sense is, for most companies that we've looked at least, 20 to 30% of their software portfolio, of the 1,000 to 2,000 apps they're running, have no path to quantum resilience. Now, if you're a CIO and you're planning for the future, every year you have a capital budget and you say, this is what you want to do. So if you know 3 to 5 years out that you're going to have to replace 20 to 30% of your software portfolio with quantum resilient solutions, it really isn't a problem. You just work it into your plan and you prioritize it accordingly. If you wait until a month or two before it happens, whether it's 3 years or 15, you're going to be in a world of hurt. And that's really the focus right now on something productive and useful we can do, which is that quantum resilience planning.
Okay. So I guess that's how companies can prepare themselves for Q-Day, is by getting set up now as opposed to waiting until it shows up. Is that correct?
Yeah, the first thing really that companies need to do is to assess their current portfolios and say, what we do, the work we do, we've developed a maturity model for doing this.
Mhm.
In the sense that we can come in and we can do this assessment. It's part of what we offer. But I'm not here to pitch that. What I'm saying is you need to do that assessment and say of our software portfolio, which which of my applications are already quantum resilient, which have a roadmap, in which case I just need to monitor and make sure I update when that's ready. Which am I going to have to plug and which am I going to have to replace? If you know that now, you go to your board and say, here's a 5-year roadmap. You're going to look like a very forward-thinking CIO, and you're going to be on top of it. And by the time it becomes real, you're going to have to, you're going to be ready.
What are the broader implications of quantum computing on society likely to be?
It's a great question. It's something that I'm now getting asked a lot. And again, I always look for the past for keys to the future. If we look at the internet, okay, the internet, arguably had led to the greatest amount of poverty reduction in history. In 1990, I think it was 38%, according to the World Bank, of people lived in extreme poverty. By 2015, so 25 years after the internet became commercially viable, the number of people living in poverty fell by 76%. There's no time in history when poverty has fallen that drastically. Now the key. There's two, and again, this is all empirical. There's two ways that of poverty reduction that actually work. One is educating women. And the other is labor mobility, if people can go to the jobs. So what the internet has changed is now jobs can go to people. Okay, so that has dramatically improved the lives of 2 billion people, roughly. Okay, but in the process, it's destroyed the lives of about 100 million people. Through outsourcing and all the effects of globalization. Now we can argue, well, we didn't know that because, like I said, this has never been happening. So we didn't do a very good job taking care of the people that have been disrupted. So we didn't know that then. We do know it now. Okay, so we can accurately predict that quantum computing is going to have, when it becomes available, whether it's 2, 3, 20, 30 years out, is going to be massively disruptive. We can probably predict who it's going to disrupt. And there's going to be so much wealth generated in the process, as there was with the internet, that we should be able to do a much better job identifying who's going to be disrupted, who's going to be displaced as a result of the changes, and doing something to make sure that we're looking after those people. And that's really where a lot of the public policy work, or actually it's work. That's probably hyping. The thinking about the public policy work that needs to be done is going.
All right, let's move on to Dr. Keeper Stanley. Sharkey. Yeah, let's move on. Can you introduce yourself and tell us a little bit about what you do and all that?
Am I audible?
Yes. I can
Okay,
hear you.
wonderful. Thank you so much for having me today, Helen and Tom and everyone else. It's good to be here in the same space. I have a PhD in quantum chemistry, and my lifelong effort has been to understand the mathematics behind quantum mechanics and its application in understanding highly accurate chemical states of matter. And this was prior to sort of the revolution of quantum computing. So this was all done with classical computers and high-level mathematics. And in 2018, I decided to start my own company called Ode L3C, which is a low-profit limited liability corporation that focuses on social aspects of quantum. So lots of education, outreach, including writing books and so on and so forth. So that's been a really interesting pathway for me. I have been involved in other public outreach forums such as IEEE and their next generation connectivity systems research on a subgroup for quantum systems, SC10, where as a group we wrote a PAR, project activity request, to create standards for a quantum cybersecurity framework. That was voted into acceptance last year unanimously with very few changes, only punctual change, actually. And then I've also been involved with the InfraGard, which is focusing on critical infrastructure sectors as defined by CISA. And they are a public-private partnership with the FBI. And I'm actually leading a new group there called a Cross-Sector Council for Quantum Technologies and Cybersecurity. In the last year, I've spent time working with a group out of MIT, Massachusetts Institute of Technology, where we talk about a concept called the quantum tortoise and the classical hare. And I can go more into that project and what that actually means for quantum computers. And, Bob Sutor kind of spoke to this a little bit, so I can add some clarity around that as well.
All right. Since you have a unique perspective on this subject, how do you see quantum AI transferring fields like molecular modeling, drug discovery, or material science? Are there specific breakthroughs that excite you?
Yes, actually, I think that there are quite a few breakthroughs when it comes to chemistry applications. And there's some really interesting AI applications that can be used to enhance the quantum computing realm. But before I go into those chemical applications, I'd like to kind of touch on what does quantum computing really mean in my mind. And quantum computing really means that we have access to a new kind of computational space. And because of the classical, the quantum tortoise and the classical hare problem, what that's really saying is that classical computing was actually optimized in a very specific way, and it's quite efficient and fast. And the issue is, unless you have a sufficient number of qubits and access to that computational space, quantum computers are actually quite slow at what it is they do. And that's why, Bob was saying, if you have a very small data set and you don't have to do too many computations, because what happens is as you start to build these quantum algorithms, the gate depth becomes too great, you start to lose information, and it doesn't become feasible. So there's two concepts to kind of think about. And the first one is a quantum advantage. So at what point do you have a problem size large enough that the quantum computer can solve it more efficiently than a classical computer? Okay. And the second one is a quantum economic advantage. So in other words, how costly is it going to be to build that computer, that quantum computer, to process a problem that's large enough that it actually gains an advantage? And that actually pushes the curve out a little bit because it's quite expensive to build these kinds of technologies. And so the problems that, if it can solve a problem for chemistry, that offset of the financial benefit for solving those problems on a quantum computer have to balance out. And so quantum chemistry algorithms has been quite the focus in terms of AI and understanding how these algorithms can play out on a quantum computer. But I will say that a quantum computer cannot invent new information. Okay, so if we feed the quantum computer a classical equivalent of an algorithm, it will not come up with new information. Okay, so if we do a side-by-side comparison of a classical computation and a quantum computation, we should expect to get the same answer, generally speaking, unless we find a way to come up with more accurate algorithms. Okay, so we have to, in the chemistry world, understand the level of accuracy that it is that we want in a calculation and how we can move beyond standard approximations that were only accessible in the 50s and 60s due to the current computational standards that we had at that time. So in terms of AI, there's many different kinds of AIs, okay? We have large language models. We also have algorithms for robotics and so on and so forth, which are different kinds of AIs. Now, what's really cool is that we can actually leverage AI to learn something about quantum computing. Okay, because it takes a long time to understand what quantum is in the first place, generally speaking, the idea of a qubit, what is superposition, all of these different quantum mechanical hypey terms, right? And so the idea becomes that we can actually possibly use the AI algorithms to learn what quantum circuits are actually useful for, right? Because now we can actually process a lot of data with AI, and we might actually get something that's more pattern recognition for understanding how a quantum computer can be enhanced, created, built out, optimized, and especially when it comes to the error correction and reducing the noise to have a nice computation for a quantum computer. So in terms of chemistry, one of the chemical industrial applications that I think would be really useful on a quantum computer, especially if we have enhanced algorithms, would be the Haber-Bosch process for creating ammonia. And I'm not the first one who said that. There's lots of people out there in the ecosystem who want to, focus on this. There was a nice paper written by a group out of Zapata that actually, unfortunately, recently closed down last year. But they had a nice paper on understanding catalyzers in ammonia processes. So this is all really cool stuff, right? But what's even better is being able to minimize the impact on Earth. So we want to, go to a more sustainable society, and we want to have access to chemicals. One of the things that I've been talking about most recently in a new book that's actually coming out in a couple months, it's called Survival in Space. We talk about how we can be using chemistry in space to be growing crystals in the microgravity environment for pharmaceuticals, also space mining and so on and so forth. And we can use virtual reality to help astronauts control these systems in space, and then we can possibly bring back resources to Earth. So that's another really interesting application when it comes to AI. Also, it has the cybersecurity aspect to it in the sense that we're talking now about intergalactic communications and security and everything else. And one more point I'd like to make about all of that is we move into space for space exploration, specifically when it comes to manufacturing products and goods in space. We're going to have the transfer of goods, which means that we're going to have to create a currency called for space, and we can call it, some kind of coin, Cosmo coin for space, right? So that we can make efficient transactions. And that would be similar to like a blockchain, secure blockchain technology. Okay, so with that, I could take another question. That was a lot.
Sure. Quantum AI holds immense promise, but widespread adoption comes with challenges. Based on your work in quantum technologies and cybersecurity, what are the biggest hurdles in integrating AI into real-world applications today? What steps should industries take to prepare for that shift?
So I believe that there's a couple things when it comes to AI. Most people right now are thinking about large language models, right? And so I think that these large language models can be seen as a threat because now they can probably produce very efficient codes, malwares, attacks. It's going to increase the number of attacks we're going to see in systems. But my argument would be that the most vulnerable point in any system is the human. So humans have to be educated. They have to understand when they can recognize something that is an attack and to not fall for clicking on a link, right? That's the biggest one, phishing attacks, right? So, we have to just have a better way to, communicate. So that comes down to, quantum key distribution, post-quantum cryptography, and all of these other kinds of algorithms. So we always go back to the algorithms. I think that there are some people out there that would debate whether or not AI is an algorithm, but I think it is. And it just depends on how much information that algorithm is bringing in, what kinds of algorithms it's leveraging. And in terms of being able to possibly build a more efficient, quantum computer, I think that these AI algorithms can study, let's say, a random sequence of circuits such that just like a large language model, when it's studying a bunch of paragraphs, it does a random deletion. And so then you can go back and randomly delete parts of the circuit and see if it actually creates a new circuit. Is it useful or did it just fall apart? And, we can then also use AI to understand when a threat might come in and how to protect ourselves from those threats, right? I think that, AI is like, it's so cool right now. Everybody's using it or talking about it and wanting to kind of push it forward, but there's still a lot of flaws when it comes to AI algorithms. And for instance, if you use a chat algorithm like ChatGPT or, Grok or Gemini, sometimes it'll invent things that you didn't want it to have and it'll forget stuff. So you have to constantly remind it, don't forget to do this, or it's okay, you can forget about that now, right? And you have to train it. But what's even more exciting about the language tools is the fact that you can get them to communicate with one another. And now you can have AIs having conversations amongst themselves. So that's another really interesting aspect of AI that I think is going to be fun to see as it comes out.
Yeah, I actually saw something like that where a laptop and a phone were talking to each other and they switched to a different language so they could use less computing power.
Right.
So, okay, how about Alan? Introduce yourself and tell us what you do. And
Hi, this is Alain Chancet, calling from France. Thank you, Tom. Thank you, Helen, for having me. Greetings to my fellow panelists. I co-founded, I'm the president of Molket SAS, a startup which I created, co-founded with Taha Selim. Taha has a PhD in quantum theoretical and computational chemistry. I'm not an academic. Molket is also a recent member of both QEDC and QUIC, QUIC. We offer management consulting and AI services in quantum molecular dynamics, cryptography, neuromorphic computing, with cloud-based hybrid classical HPC, classical quantum HPC, and also quantum computing platforms. I'm also an advisory board committee member of the North America Technical Institute, NATI, in Virginia, USA. I'm well known in the IBM quantum world. I'm a Qiskit advocate. I took part in a number of hackathons since 2020. I've been invited as a co-speaker or speaker in a number of events, mainly around AI-driven quantum molecular sensing for cybersecurity. That was for the Quantum Security and Defense Working Group in November of 2024. also attended the IBM Quantum Developer Conference in New York in November of last year. And a few days ago, I had the privilege of making a presentation for Qubit Hub. It's a quantum computing hub in Mexico, and the topic was AI and AI agents in quantum chemistry simulations. In May of this year, I will I'm an invited speaker at the 2025 IEEE, the 14th ICCCAS in Wuhan, China, but I will present remotely quantum permutation pad with Qiskit runtime. And quantum permutation pad is an example, an illustration of a quantum algorithm for cryptography, which can also be implemented classically. And recently there has been a post by Randy Kuang, who is the inventor of quantum permutation pad, about combining QPP with some other algorithm to provide a smart random number generation. So I'm pleased to be with you today and open to your questions.
Yeah, how do you talked about AI agents? How do you envision quantum AI agents will be a giant step for humanity or something else?
So my view complements the views which have been presented by the other panelists so far, and that's really convenient because my view is that and as Dr. Kipper and Sharkey pointed out, LLMs are quite popular and successful, and I would like to point out that AI agents seem to take the lead in terms of providing some reasoning abilities. And my proposition, Moltke's proposition, is to extend the concept of AI agent to quantum AI agent. By that we mean agents that leverage not only quantum processing and AI, but also, and that's really important, quantum sensors, quantum communication, to do what? Well, to interact with their environment, to collaborate with their peers and humans, of course, to make decisions, and act, and that's the definition of an agent, autonomously or semi-autonomously to achieve specific goals. So that's our vision that in the coming, it's happening now. It's just a logical extension of the success of AI agents by including in the mix, if you want, quantum processing and quantum sensors. It's also a logical extension of what has been achieved recently by IBM, for instance, combining HPC and quantum computing to model fairly large molecules, and the offering from Quantinuum, which adds to the mix of HPC and quantum generative AI. And so, like Bob Sutter pointed out earlier, we in our view, we should think about quantum and AI as part of a bigger workflow, where there is synergy between high performance computing, supercomputing, quantum computing, and AI. That's what we put forward. That's our vision.
Can you provide some examples of how quantum AI would be used?
Yes, so today we have a very in production AI-driven autonomous chemical synthesis robots, where we just need to add quantum sensing, or why not on top of that quantum processing, maybe combining synergy of quantum sensing and quantum processing. So these quantum AI-driven autonomous chemical synthesis robots, they could assist chemists in discovering and creating new materials. So that's the first application. Another one, and that extends on the presentation. I was a co-speaker with Taha Selim and also Joe Radix, who is among the participants. One application pertaining to security is detecting wiretapping of fiber optic cables using quantum chemical sensors. Now we can think of autonomous robots that achieve that and would, in addition, collaborate synergetically with other robots via quantum secure communication. Now, the third kind of application would be for drones or space probes. So we can think about autonomous drones or space probes that would integrate quantum processors, but also quantum sensors and communication components with conventional AI systems. And that would be for defense and space exploration. So that's an example where the intelligence, if you want, the brain would be a conventional AI system, but it would be supercharged with the extrasensorial abilities thanks to quantum sensors. And the idea is that over the next couple of years, the value added of the quantum processor would gradually, hopefully, increase in this synergetic combination of quantum sensors, quantum communication, and together with AI. So these are just 3 examples, but there are many more.
Okay, I want to open it up because there's a lot of questions in the chat. And I think you said something, Dr. Suter. You know, said, can you clarify in your comment that quantum is good for problems that don't require much computation? Somebody was wanting that better clarified.
Sure. And that is a today statement, just to be clear. So what happens is, so the core piece of information that the way we model quantum information is in what we call a qubit, a quantum bit, right? Mm-hmm. And this is where we get these phrases like superposition and so forth. It's much more sophisticated than just a plain bit. Now, we can either manufacture qubits. So, for example, IBM does Josephson junctions as qubits. And there are different ways of doing this that is actually making things on a chip. Now, another way of doing it is to use natural things that have quantum properties. So photons, for example, and electrons attached to atoms that could be neutral atoms, cesium, rubidium, there was a question like that, and others, strontium, or ions. And people that do trapped ions like ion Q, quantinium do that. But somehow, some way, for the natural things, you're probably going to have electrons or photons entered into this. Now, these are quantum mechanical things, right? You know, let's stick to the natural things. If they existed in a perfect void, there'd be nothing to interfere with them. That is the information we would store on them, the quantum information. They would just stay there perfectly forever. But you can't have a quantum computer where you can't talk to the things in there, right? There are wires going in, right? But for some of these modalities, like superconducting, this is why we have these fridges, right? Close to absolute zero, superconducting wires. They try to very close manufacturing tolerances so that nature itself doesn't interfere with what we were trying to do with these specific qubits, either natural or manufactured. But it's not perfect. And so,
okay, this is, oh, go ahead, finish up.
Well, so I was going to say, so first of all, the environment's trying to mess up your computation, but also there are things like if I talk to one qubit, right, I send it an instruction to do something, right? It may actually affect a nearby qubit, right? So it may cause a little bit of an error, a little bit of noise going to that nearby qubit. So what happens in these computers, right? First of all, the qubits start to degrade. It loses the information slowly, right? So that's one thing. But also as we're doing stuff to the qubits, actual operations, calculations, errors are getting introduced. So after a while, what you think is good information by just sitting there and doing stuff to it, it's getting worse and worse and worse. And at some point, the information is just garbage, right? So that's the limit. That's why you can only do so many things. Now, depending on your modality, you might have a little bit longer, right? But it is the reason why we must go to error correction protocols.
Okay. Now this, I'm going to throw this out for anyone to answer, but DK says, if this is the case, then can a network or cluster of quantum computers solve the scalability problem? Al?
That's well, there is much hope that this is indeed the case. However, I mean, I'm aware since I've attended the IBM Quantum Developer Conference in 2024. IBM, for instance, bet on interconnection with, I think, fiber optic of modules of a reasonable size, and so it better work. Okay. And there are experiments which are really promising. And what's amazing is that it's not just really local to make a quantum-centric supercomputer work, but also there are promising experiments that could lead to a genuine quantum internet, where these clusters could be gather quantum computing units, which would be geographically fairly far away from one another. So I guess Bob or maybe Dr. Kipper Sharkey would have more to say.
If I could just, so last week, Microsoft introduced its Majorana 1 chip. And there was a little controversy because Majораnas have been controversial for a year. Have people actually seen these special particles? But nevertheless, they claim their chip is, let's say, 1 to 8 qubits, depending on what sort of conversation you're having with them. Amazon announced for Caltech that they have 5 qubits. Right? IBM has gotten up to about 1,100. Some other people have gone to 1,100. You know what a good number is for the number of qubits to actually do something useful? Good minimum number, 100,000.
Oh.
Okay, 100,000. So when Google came out in December with 105, and people said, the world's ending suddenly, right? And it's like, they have 105 qubits, and we need 100,000. And by the way, that's conservative. Right? If you talk to pharmaceutical people, they will say, we need 9 million just to get started. Now, people will argue about error correcting codes and this and that, whatever. But the point being is that any of these ways of doing it, and like what you're saying with IBM, they can only fit so many qubits on a chip. They went up to about 1,100. They've dropped down to about 150 something. They will microwave quantum networking chips on the same board, right? Think of it that way. Right? But for other modalities, trapped ions, neutral atoms, and things like that, especially trapped ions, they can fit a few dozen qubits in one unit, one device. So the only way you're going to do it is by networking a whole lot of these together. And for some of them, like trapped ions, they need it real soon. For others, neutral atoms, they can maybe get to 1,000, 10,000. They can kick it down the road a little bit. But ultimately, as I said in the comment, we will only create big enough computers by networking little computers. They may be homogeneous, they may be heterogeneous. We make it really smart and say we actually have to mix different types of qubit technologies to do real world application.
Okay, next question comes from Thahil. I hope I'm pronouncing your name right. Is anyone aware of any specific quantum algorithms that are promising for the usage in Gen AI?
So yeah, I saw I think it was Bob who commented
Oh, okay. Yeah.
that yeah, I think it was Bob who commented about it being more of a deep learning than Gen AI. Even some basic classic machine learning models could play a role, because it's ultimately, for these use cases, it's about the size of the data set and the number of factors, which in theory, when quantum computing reaches a certain computational level, you can, radically reimagine. So I don't think that, LLMs in particular may be the right tool, but just the scale at which you could do it may fundamentally change as a result.
Okay, DK has another question. How will traditional software program different on quantum computers?
Completely. That's easy. The quantum computing model is just completely different. If you do code, right, and if you do assignments, you do if-then tests, you do loops, all this sort of stuff, congratulations. None of that works in quantum computing, right? It works in maybe a classical framework that is controlling stuff that's going on in quantum computers. And one of the fundamental problems is, and this is the strangest thing when I was learning quantum computers, I could not believe this was true. It's called the no cloning theorem. I put information into one or more qubits and I say, Tom, I want to give you a copy of my information. And I can't do it. I can give you the actual information, but it would destroy my copy simultaneously. And this is why people talk about teleportation, right? That's where that comes from and things like this. So how the heck are you supposed to do computing if you can't copy information? Forget your quantum database, right? You load up all your information in a database. Every time you pull it out, it destroys it, right? What are you going to do? But there are other things. There's entanglement. There are other techniques like interference. The actual instruction set is much, much more sophisticated than what you can do. So I have learned, so just to fix ideas, I am in my 60s. When I learned quantum computer, I had decades of classical computing to unlearn and to think a certain way. People who learn quantum when they're younger don't have this problem. Computing is computing. I have met 12-year-olds who are brilliant in quantum computing, right? So open it with fresh eyes, or look at it with fresh eyes. But if you're learning it, understand, you'll go forward, you'll feel smart, then the next day you'll feel dumb, but then you'll feel smart again. And eventually it'll all sink in.
Tom, I'd like to throw in a couple of points.
Okay.
Yeah. Probably I'll start from the freshest one from today. Amazon Web Services announced on Thursday, which is today, new quantum computing chip called, is it OSCILAT? Those who know, correct me. And I will just read. OSCILAT represents a breakthrough in the pursuit of building fault-tolerant quantum computers capable of solving problems of commercial and scientific importance that are beyond the reach of today's conventional computers, the company said. So basically, they claimed that the chip can reduce the costs of implementing quantum error correction by up to 90%, kind of getting back to the cost-benefit analysis that we mentioned, addressing the really the unimaginable price that quantum computers require to invest. However, when we think about the energy needed for traditional classical computers, and when you hear about the likes of Stargate projects that recently was announced, like $500 billion investment, you will remember from the White House Oval Office, this magnificent presentation, and then DeepSeek barraged into the headlines with their news. And this is actually what prompted me to think about what would be this golden key. Could it be quantum integrated, not into one process, but maybe phased the combination of the strength, the power of quantum and AI? So Majorana now is kind of skeptically discussed their claim of 1 million chips, right, Bob? You were the one who commented that you want to see like 50,000. So this is something I wanted to kind of leave with you all to think about maybe for our next discussion. And another point that I would like to raise is the complexity of understanding, comprehensive for us non-quantum physicists, not for computer scientists, but people who have to integrate both quantum and AI, and I'm sure in the future it will be a must, like the internet today, right? I would compare it to like tenure track, those of us who have been in academia, it's you publish or perish. I would dare to extrapolate and suggest that if you don't educate yourselves now about the quantum and AI, your companies will fall behind. And this prompts me to call your attention to Bob Kirk, who actually contributed to our discussion today by specially presenting and recording a presentation on quantum and AI. And Bob is the chief scientist of Continuum. So please take your time, explore his presentation. On top of everything, he composed and recorded music using quantum instruments. So if Bob would be participating in our discussion today, he's delivering a keynote address in Dubai today, so he could not be online with us, but check out his presentation. And Bob Kirk was the one who actually introduced the concept of pictorialism in quantum. I heard his presentation for the Royal Science Institute for non-quantum physicists. And it was fascinating how they had the experiment and educated school children. In 2 months, these school children who invested allegedly, I refuse to believe this is physically possible, but they recorded this as an experiment, that after, I think, 2 months, the Skyfall kids were able to pass the Oxford postgraduate quantum physics exam using the quantum pictorialist concept and textbook that Bob Kirk and some of his collaborators created. So I highly encourage you to look into this concept of simplification of quantum through pictures. The book that Bob Kirk and his colleagues published is fascinating, but the presentation, which you can find on YouTube, and if you wish, send me a message in LinkedIn, and I will send you a link. So I'm talking about the 2 presentations of Bob Kirk. First is generally about quantum and AI, which kind of hooked me, triggered, my jaw was on the floor. So I invited him to present. So he recorded the presentation and composed the music for us. But there is another presentation, which is really like general about the concept. I encourage you because it's easy to follow. And certain things become much more clear for us non-physicists, those who are not familiar with the quantum mechanic, but I think all of us in business, it's kind of a must to start learning it now. Otherwise, our competitors will leapfrog, and it's like today we would refuse from using the internet. So I believe that in reality, quantum and AI is much broader deployed already today. It's in the areas probably of defense and space where it's highly classified, and we in the lay public are not familiar, we will not be informed because there is the race in quantum and AI and the bitter lesson of OpenAI when everything became readily available. So what some are referring to as adversaries can openly use. It is frustrating for those who invent the technology and then kind of start losing the cutting edge in this competition. So we need to understand that the technology is already here. We cannot deny its potential. When it will become deployed as kind of industrial technology, if I may, when it will be scaled, it's like with Gen AI, nobody really knows. But it's already here in some extent. And I'm so grateful to all of you for participating and, some on a ridiculously short notice. But I couldn't pass this subject. We initially intended to have cybersecurity as a topic today, but I just thought it's so hot. We need to touch it now. And it's kind of scratching the iceberg, beginning the conversation. But it's probably one of the most fascinating, topics to discuss and watch for going forward. The, this convergence of quantum and AI, which we cannot throw into one bucket, but definitely there is synergy, and the applications are already ongoing.
Okay, Dr. Sharkey, you have a statement or
Yeah,
something?
I just wanted to kind of follow up with what Helen was just saying about education. I think it's so important for the older generation. I'll just, kind of divide it up into, we have children in grade school right now, they're learning topics, and then we have anybody older than that. And they should be learning about quantum. They should be educating themselves, but it is a very difficult subject, generally speaking. And by the time quantum, gets developed and actually is integrated on a computer, the way we integrate with it may not be at the qubit level. So we will have software packages and languages that we'll be able to kind of communicate with. But I would say that is in terms of our kids learning about this topic, it's really easy to integrate quantum information science, generally speaking, into almost any science course. So this can be done in middle school, because children in middle school, they create codes, they're working on science projects, there's lasers that they can be setting up, there's all sorts of experiments that kids can be doing to learn about these concepts. And one thing that we did put in the book, Quantum Chemistry and Computing for the Curious, illustrated with Python and Qiskit code, is that it's generally easy for somebody to kind of pick up if they learn about this in terms of chemistry, okay? Because chemistry does impact all of us. And as a company, I think it's really important to start to understand how we can be leveraging young kids in our companies through these technologies, because they're the new brain power and as Bob Suter said, they don't have to unlearn 2 decades worth of, classical computing concepts, right? So they can, so it's quite beautiful.
I would offer to at least add to this great idea and, absolutely vital process that we need to engage kids from very early on to integrate. But I used to work at the bank, and we had the basically kind of software courses, the computer science program, and we ran the experiment. And guess what? People 55 plus who participated in this educational program demonstrated higher efficiency and better results comparing to their young peers. So I would say that age is not necessarily a critical factor. I think we need to engage all. And one of the motivating factors for me was when I was creating the Global Alliance on Sustainability and AI, is to make sure that nobody is left behind. Disregarding the geography, disregarding the age and wealth status. And I think the same pertains to quantum. I know it's easier said than done, but I'm so grateful to Dr. Sharkey for bringing the kid education component to it. I would just advocate that we need to educate all, particularly now when thousands and thousands of people are losing their jobs. They need to be urgently upskilled, and this situation will only escalate further as quantum and AI will be deployed full scale. This will cause a major, major disruption, and we need to be prepared. We need to manage the risks and make sure that people continue having lives and providing for their livelihoods, for their families once these technologies are deployed full scale.
Okay, before winding this up, I do have one question, and whoever wants to can answer it. Basically, with the Microsoft news from last week, they stated that they had created a new state of matter. Can somebody explain what this new state of matter is?
I'll jump in. This is not the first statement of new states of matter. When I joined Inflection 3 years ago, I learned about Bose-Einstein condensates, which were, when they got a Nobel Prize for discovering this, were at the time a new state of matter. And then physicists discovered other condensates that were new phases of matter. This is a particularly weird type of particle that in some sense, just as we think of sort of protons and neutrons being opposite, these embody both elements within themselves without actually being neutral, so to speak. The story of them goes back to the 1930s. A physicist, an Italian physicist named Majorana, postulated the existence of this. He then got on a boat and mysteriously disappeared. So, there's kind of a strange Enrico Majorana. And they've been looking for this for a very long time. Now, the problem is that there have been a series of papers. There was a paper in Nature that went out that was then retracted. And there have been several of these. And it turns out it's hard to see these things. And when people think they're seeing them, they're actually seeing something else, right? Aside from any improprieties regarding the data. So that when Microsoft came out and said, hey, we actually built a qubit doing this, people went, well, we're not so sure, right? Because we've heard this story before. It's like the boy who cried wolf, right? I found it. No, there's no wolf. I found it. And then when they actually feel they found it. I was briefed on it. I think they firmly believe they have found it. They have to convince the top physicists that they've done it. So research will continue on this. It's fascinating. It's very, very early. They will be part of the late second, maybe third generation of qubit technologies. So for all of you who are far younger than I am, for example, whatever quantum computers are built from or made in 25 years, they probably won't be any of the above exactly for any of the things we're doing right now. So it's fascinating research, but we have a ways to go. And certainly saying, I found one, I can build a million. It's a little bit of an overstatement, but that's marketing.
Okay, well, I think we're a little over an hour now. So if you want to make any closing statement, Helen.
Well, first of all, I want to wholeheartedly thank everyone for participating. I truly believe that our discussion was very interesting, very enlightening, not just for top-level quantum physicists and computer scientists, but for all of us who are just trying to grasp and catch up with the technology being in other lines of business. So I think this is priceless. This conversation is recorded and we will post it on YouTube and encourage you to share. This is just the beginning, as I said, but this is a fascinating conversation. This is a fascinating topic. And I really sincerely, truly believe that we all will benefit from this technology. We don't know exactly when it will become widely available. But to all of you, huge thanks. And with this, we end this discussion. We will have our next event on March 26th at 2 Eastern, and we'll talk about quantum and AI in cybersecurity. So I very much look forward to welcoming you all to our next discussion on March 26th. And with this, thank you and goodbye.
Thank you, everyone.
Thank you.
Take care.